In the last nugget, we looked at an introduction to the OSI model, why it's here, why it was developed, and what it does. Now, I want to take you through the layers of the OSI model in an intensely practical example that will make them very relevant to you. So let's take this network scenario and turn it into something that a lot of people do every day, and that's go to online banking. So you're sitting on your computer, you open a web browser of some sort. Let's just say it's Microsoft Edge, or maybe it's Chrome or Firefox. You go over to an online bank. Let's just go to Wells Fargo, simply because my mom works there. Shout out to Mom. Hi, Mom. So Wells Fargo has a web server that's receiving your requests and you're doing your transfers. Let's just, again, paint this scenario, make it a little more real. We're logging into the website. We go to our checking account. We say, I want to transfer $50 from my checking over to my savings account. We type in 50, hit the submit button. What happens? Well, I want you to imagine that inside of your computer, that little $50 transfer walks over to a staircase, right? So here's the $50 click that you just did, transfer from checking to saving. And in the sign above that staircase says something like stairway to the network. And each step of that staircase all the way down has a label printed on it. So, if we go three-dimensional, this is where my drawing skills break down. This one says application layer. This one says presentation layer, so, and so on and so forth as it walks down the OSI model. And at the end of this stairway is a long river, right, that takes that $50 on a speedboat over to Wells Fargo's server, right? So here's what literally happens every step of the way down. You've got the application, which is the web browser itself, Edge, Chrome, Firefox, whatever web browser you're using that generates the $50 request. And that's really the function of the application layer. The application layer is where the network-aware application resides, right? So when you're talking about the application layer, you're literally talking about the application that's generating the data, right? So you put in the $50 transfer, Edge, Chrome, Firefox generates that request. Okay, it hands it down to the presentation layer. And this layer is where it generifies that request into something that's a little more standard. For example, things that you'll find at this layer are standards like HTML, standards like JPEG for a picture, standards like MP3 for an audio file. Why? Because we've got all these flavors of web browser, right? Edge, Chrome, Firefox, all these kind of things. And how many web servers are out there? A lot. There's IIS in the Windows world. There's Apache on Linux. There's IBM has one, a WebSphere. There's all kinds of different web servers that this could be running. We've got to have some common ground, right? That's going to work between these two websites and that's going to understand that $50 request. So this is where you have the generic standards, or think of them as like formatting the request in a way that anything could understand. Now, actually, great example. We're talking about a $50 transfer. Is that something you would want to be secure? Yeah, I definitely would. I don't want somebody to see how to get my $50 transfer going across. So what would we use? Encryption to scramble that data as it goes across the network. Well, the fact is it's using generic encryption. I know that sounds scary, like, oh no, generic encryption is bad. Actually, it's the best because it's an industry standard encryption that everything supports. It's open source, so people know how it works, and they know, by golly, that thing is secure. So the presentation layer formats it and encrypts that data so no one else can see it. But at the other side, the web server has the encryption keys to unlock it. Okay, so we generated the $50 request. We generified it, so it became a generic web request that the web server on the other side can understand. Now we drop down to the session layer, which is probably the simplest one and the one we deal least with because it's the one inside the computer that starts and ends the session, that manages the session, does keep alives, all those kind of things to keep the session running. In our case, this already would have happened to get to the point where we were clicking the button to do the $50 transfer because we would have already started a web session with the web server. Now, on your paper, because I know you're taking notes and jotting furiously everything that I'm talking about, I want you to draw a line right here, right? And put these top three layers inside of a box. And inside of that box, you would call it the computer. Because usually, network engineers like you and I do not care about those top three layers. Meaning, if it's a problem up here, It's not our problem because it has nothing to do with the network. It has something to do with the application. And welcome to the war of two worlds, the war between the system admin and developer and the network engineer. A constant battle where our fingers are being pointed and they say, it's a network issue. And the network engineers are going, nope, I can ping it. It's an application issue. So that's really where those top three layers come from. Matter of fact, I'm going to talk in the upcoming nugget about the TCP/IP model, meaning they actually call that the DoD, Department of Defense model, where the people who created TCP/IP tried to create their own model as well. It's not as good as the OSI model, but what they did do is they grouped all of these three layers into one big application layer, right? They don't even separate them in the TCP/IP world because from a network side, we don't usually care about them, right? So, okay, line drawn. Now let's look at the stuff we care about. We'll clean it off so we can focus on the super important network engineer stuff. The transport layer. This layer has two major functions. One is to pick your protocol, and two is to pick your port. Now you might be thinking, well, I thought we used TCP/IP. Isn't that our protocol? Well, remember, TCP/IP is a suite of protocols. If we were to unpack this thing, you'd find out it's like Microsoft Office, right? When you say, I'm typing a document in Microsoft Office, people would kind of scratch their head. They're like, well, Microsoft Office is a suite of applications. Do you mean you're typing a document in Microsoft Word, right? The sub-application inside of that suite? Well, it's the same thing with TCP/IP. A lot of people just say TCP/IP, not even realizing it's a whole family of protocols that work together. For example, TCP and IP are two different protocols. So at the transport layer, and I'll show you 90% of the time in the world, we have a major choice between TCP and UDP. Now, there are other protocols that exist at the transport layer, like ICMP, like IPsec, like there's all kinds of different ones that are out there, but the vast majority of our applications use one of these two. This is the decision between reliability and speed. And keep in mind, you don't choose this, I don't choose this, the application chooses this. So Microsoft Edge, we'll use that as the web browser because it's the shortest name to write. Microsoft Edge, when the developers programmed that application, they said, okay, when you connect to a website, I want you to use TCP, so you will be a reliable connection. Okay, what do I mean by reliability? That means when I start this session with this guy, first off, it's going to do a three-way handshake, which I talked about in a previous nugget, to form the session, to form the TCP communication, and then every single time it sends some data, say that $50 transfer, sends it across, the web server has to reply back and say, "ACK, I got it. I got it. Yep, I received your data transmission." So this computer goes, okay, good, that $50 transfer went through. Whereas if it didn't receive that ACK back, it would go, oh, that must have dropped somewhere in the middle. Maybe we had a solar flare or something, right? So it's going to resend that data and make sure that it gets the ACK for it received. That's what TCP does. Now, what about UDP? Why on earth would you ever choose an unreliable transport? Why do you want speed over reliability? Well, for real-time communication. So when you're having a Skype call or a voice over IP conversation, or you're streaming music or movies, or any real-time communication, UDP is awesome because there's no point in resending real-time data later. You're having that conversation. Let's say we're talking. We wouldn't be talking to a server. Actually, I do sometimes talk to a server. I'm like, hi, server, come on, please boot, please load, don't crash, right? I'm having this conversation, and these packets are flying across. Let's say this one was dropped where I'm going, please. There's no time, there's no use in resending that please at a later time because the time has passed. So those real-time programs would choose something like UDP. Now, the second thing it does is choose a port as well. How many things, I'll ask you this question, and you got to be honest with me. Confess your sin to me right now. How many other things are you doing in addition to listening to me right now on your computer? I know nobody is, because this is so engaging and you want to know this, but many people like me would have 50 different web browsers. I'm flipping around on the bottom of my screen. So many different web browsers open to different things. They're streaming radio. They're checking news headlines, sports scores, everything else. All of that's coming in one network card, right? How does the computer differentiate between all of those different input streams? It uses a port. So whenever I open my Edge browser, right, and I say, okay, I want to go. Matter of fact, let's do it together. I'm gonna Let's open Firefox because that's what I see right there. And right there, I went to a web page, right? Firefox.com. I open another tab, and I go to the Mozilla Developer Network. Another tab, I go to cbtnuggets.com. And another tab, you see what I'm doing here? I'm creating all these. Another tab, I go to msn.com, where I get the latest news and everything else. So now I open a command prompt, and I type in a simple program, netstat. This program shows all of the open connections from my computer to other things. Now, let me grab my pen here. This is the foreign address, right? I'm accessing all of these. So you can see I'm going to LAX. So, I went to MSN.com, and behind the scenes, MSN.com redirected me to whatever that server is, :HTTPS, right? That's the protocol that it's using. But look, more importantly, right now at my side. This is me, my computer, 10.225.1.132, 59.277. What is that? That is the port number. And actually, it's the source port number. This is the destination port number. Because over here, this server probably has many different things running in addition to the web server that it's being, right? I'm going to Wells Fargo or MSN.com or whatever it is. So it could have many different things that are running. I need to make sure I tell it I'm going to the web server service on there. And that's what the destination port does. And I'm coming from this web browser window. So literally this web browser, or this tab of my web browser, is assigned a unique source port. So when this web server transmits back to me, my computer goes, oh, you're going to that tab because I assign that tab. We don't do this. The computer does it. I assign that tab behind the scenes 59.277. So when I see that incoming data for 59.277, because it's actually in the transport, it's behind this picture. It's in the transport layer of the OSI model. Because I see that, I'm going to send it right back to the web browser window. Let me turn off my pen. Hang on, bring this back up. And you can see now that it's continuing to go, my computer's going all over the place because every single time you go to a website, like you and I see the website of MSN.com, right? And you see that little box showing, I don't know, the Olympic runner or something like that. Over here is an advertisement. Over here is something else. These are all coming from different servers all around the internet. So going to one web page may start 50 different sessions for you and 50 different port numbers that are assigned at the transport layer. Man, it's amazing this can happen so fast. So where are we at in our journey down the network staircase to reach the river? Right? We chose to transfer $50 from our checking to our savings. We submitted that in a network-aware application like Chrome or Edge or Firefox, which packaged up that $50 transfer as the application data, generified it, encrypted it so the web server would understand, ensure the session was started with the web server. Then it chose to use a reliable transport, TCP, to ensure that that $50 transfer is received at the other side. And it used ports to segment that communication. So when that $50 transfer is received at the web server on port 443, which is HTTPS, it knows to send it to Apache or IIS or whatever web server program it's running. And when it sends back to my computer, it sends it back to the source port, which this guy dynamically generated. We'll just say 55970. So this guy knows which web browser window to put that information back into. Now the computer needs to add on the information that tells that $50 transfer where it's going. That's the job of the network layer. That's the IP address that we're going to. Now, you might remember from some previous nuggets, I said the IP address is the end-to-end address, meaning it tells where that data originally came from and is finally going. So let's say this guy's IP address is 10.1.1.5, and this web server's address is 4.1.1.1, right? So two different addresses. This becomes the source address where it originally came from, and this one becomes the destination address where it's finally going. That is then added to the packet that's being generated. We drop down to the data link layer, and it adds yet another layer of addressing known as the MAC address. Or many people call that the physical address because it's burned into the network card. This is the hop-to-hop address because this computer has to reach the web server, but it can't just send it out onto the network and say, go packet, find your way. It's like Lassie, right? Go Lassie, find Timmy, there's trouble. Go packet, find your way to Wells Fargo to do that transfer. No, it has to say, go to that router to get there because that's the default gateway of the computer. So how does this guy say go to the router and go to the web server at the same time? Well, that's why we need 2 layers of addressing. The IP address telling where it's finally going, the MAC address getting it straight to the router that can get it to where it's finally going. So the router gets that packet, and it goes, oh, you're coming to me because it's my MAC address, and then it looks a little deeper in there and goes, oh, you're actually not going to me, you're going through me, right, to the other side. So that's where we need those 2 layers of addresses. Finally, the data comes down to the physical layer of the OSI, and welcome to the river, my friend. We've moved down that staircase. The physical layer is where it actually sends, converts all of this to zeros and ones, ons and offs, electric on, electric off, light on, light off, and fiber optic cabling. It all depends on what kind of physical cable you're using to connect. Dictates what transmission mechanism it's using. That's where the data literally leaves the computer and goes off to the network river to find its way. This process that I've shown you right here is known as encapsulation, meaning I took that $50, that's the application layer data. It was generified, the session was started, and then we tacked on to the front of that a header that is a TCP header. And inside of that header is what ports, the source and destination ports, are being used. Then it tacked on there's a gap here because that's inside of here. I tacked on the source IP address. I tack on the destination IP address. In the end, we have a packet that looks like this. This is where you can see all of those puzzle pieces put together. This is actually a slide from an upcoming nugget where we're going to use Wireshark and actually tear apart network transmission and see these different layers. This is your $50 transfer. That's your data. There's your layer 4 information, your TCP and UDP ports. Here's your layer 3 information, the network layer, source and destination IP address. Here is your layer 2 information, source and destination MAC address. And then you notice right here, notice this is the same color as this. This is tacked on also at layer 2. It's put on at the very end. It's called a frame check sequence. Some other people refer to that as the CRC, the cyclical redundancy check. So essentially when the computer reaches this point where it has all this data in there, it runs a mathematical algorithm on all of that stuff which spits out an answer. And it puts the answer to that mathematical algorithm into the end of the packet known as the frame check sequence. What happens when it's received at the other side is it runs the same algorithm on all of that data that goes through and ensures it comes up with the same answer. Because if the answer is different from what's in the end of that packet right there, it knows that something got corrupted in here all the way through because the mathematical formula is coming out and spitting out some other answer, so it will ask for a retransmission of that data. Whoo! A speedboat down the network river. Can you even, for just a second, let your mind think about this? I'm talking about one packet, a $50 transfer. That process is for one packet, and it's happening potentially thousands and tens of thousands of times every single second a computer is running. Hopefully, I've been able to emphasize why the OSI model is so important through this discussion. As I've been speaking, you've heard me speaking the OSI. That's why I titled the last nugget that title, Speaking OSI. As network engineers communicate, they just talk like this. Oh, there's an issue at layer 2. Oh, check layer 3. That must be a routing issue. Oh, layer 4 might be a firewall blocking that port number. Understanding what I've laid out in this nugget will help you speak the language of network engineering that helps you hone in on exactly where configurations exist, where troubleshooting can be done. I hope this has been informative for you, and I'd like to thank you for viewing.